السلام عليكم ورحمة الله وبركاته. بسم الله الرحمن الرحيم. إن شاء الله today we'll start a new sub-session called Uninformed Search. We'll know inshallah maybe towards the end of this lecture why it's called that way. But if you remember last time we covered a generic search algorithm that will try to find a solution within the state space tree or the search tree by incrementally expanding that tree. And the main idea, or the main maybe couple of ideas within this algorithm, this generic algorithm, is the idea of the fringe. So we have the fringe, which is a data structure that that will have or will keep track of the potential plans to be explored in the future. And the other idea is the search strategy. And the search strategy will choose for us which node to expand next. Okay, and last time we said that we don't care about it within the search, within the general algorithm. But today, inshallah, we will study at least 3, I hope 4 search strategies. Each one will tell us how we select the next node to expand. Okay, so that's the context of today's topic within what we started to explore last time. So we will inshallah cover 3 or 4 algorithms today, or search strategies: depth first search, breadth first search, and what we call uniform cost search if we have time. So the first one is depth first search, and I'm quite sure that you heard about this before in data structures and algorithms courses. So in depth first search, we expand a deepest node first. So the deepest node, of course, now we are talking about the search algorithm. So the node that we will expand next is the deepest node. So let's see an example. If we have, remember this state space from last time, we start by adding the start state to the fringe. So the fringe now has one state. Remember, this is the whole search tree, but we don't expand it at once. Okay, so this is just for illustration. But what we process at any time are the nodes that are circled. Okay, the highlighted will be the ones that were in the fringe but we're out of the fringe now, and the ones that are not highlighted are the ones that are currently in the fringe. So currently we have only one node, so we don't have any other choice other than expanding it. So we expand it to D, E, and P. Now, which one we should choose to expand next to get out of the fringe? It should be based on DFS. It should be the deepest one. Now, all of the 3 has the same depth, which is 1. So we will choose one arbitrarily. Let's say that we'll choose always the leftmost one, or the one that is higher in the alphabetical order, okay, or first in the alphabetical order, which is D in this case. So let's say that we will select D. Now, once we select D, we'll expand it to B, C, and E. Okay, now we have 5 nodes in the fringe. So which one we should expand next? Any answer? Okay, Ghanem, please raise your hand first. Okay. Any answers? Any other answers? Okay, Ghanem. Which E? The one after D. You mean let me show. You mean this one, right? At depth 1, not at depth 2, right? Oh, this one. Okay. So why is this one specifically? Why is this one? Yes, but we have B, C, and E all have the same depth here. Okay, and arbitrarily we choose the one that comes first in alphabetical order. Let's assume that we take this tie break rule here. So in this case, it won't be E, it will be B. Okay. Yes, more B, C, and E are at depth 2. E and P are at depth 1. So we choose one of these three because they are equal in depth. Okay. So the next one will be B. We'll expand it to A. Now we have 5 nodes in the fringe. Which one should be expanded next? Faisal? Faisal, we don't hear you. Faisal? Audio is not working. Type. Anyone else? Okay, I can see what Faisal is saying, but I want someone to talk to me. Thanks, Ghanem. Someone else, please raise your hand if you want to answer. Anyone? Abdurrahman? We'll go for a Y. Yes. It's no. There is a choice. You mean there's no other nodes of the same depth? Yes. So A is the deepest. So we should expand A. Now, if we select A, it has no children. Okay. So we go back to the fringe. Now the fringe has C, E, E, P. C and E now are at the same depth. So we'll select C. Okay, because it's based on the alphabetical order, it comes first. So we will expand C to A. Now A is the deepest, so we'll take A, and so on. Okay, so we'll always go deep. So after A here, we'll have to expand E, then H, then P, then Q. Now we are done with, there's no leaves of Q. We go back to this Q. No leaves of this Q. We go back to R, then F, then C, then A. Okay, now we no children for A. Then we have to go to G. Now at that point, remember, whenever we take a node from the fringe, if you remember the algorithm from last time, whenever we take a node from the fringe, we check whether it is satisfying the goal condition or not, or the goal test or not. So of course G is the goal state, so it satisfies the condition. So now we have a solution which is S, D, E, R, F, G based on DFS. So DFS will find that solution, okay, using the DFS strategy. Okay. Now, question? Okay, thanks for informing me, Faisal. Okay. Okay, now so we saw now a full example of DFS. Let's talk about the properties of any search algorithm so that we can compare between different algorithms. So we'll talk about 4 properties of any search algorithm. The first one, whether it is complete or not. Complete means it's guaranteed for that algorithm to find a solution if one exists. Okay, so that's completeness. The second one is optimal, whether the algorithm can find the optimal solution or not. And we said that what we mean by optimal is the least cost. So the algorithm with the least cost. Is it guaranteed to find the least cost solution or not? If it is, we call it an optimal algorithm. And we'll also think about the time complexity. How much time it takes to find the solution. And in this case, of course, it would be in order of the number of nodes that we process until we reach a solution. Space complexity, how much memory it needs, again, in terms of the number of nodes that we will have to keep in memory before we reach a solution. In doing that, so these are the 4 properties that we will examine for each algorithm: completeness, optimality, time complexity, and space complexity. And in doing that, we'll use kind of a cartoon for the search tree. So we'll assume that the search tree is like a triangle. Of course, when we go down, the number of nodes will increase exponentially. So this tree in reality should be much wider than this at the bottom. But just for illustration, it's like linearly increasing in length. But in reality, it is exponentially increasing. So at the root, there is one node, of course. Then we will assume that each node, just for illustration and for the calculations, we will assume that each node has b children. So the branching factor, we call it the branching factor. The branching factor will be b, and we'll assume that it is constant just for the calculations. So that means that at level 1, we have b nodes. Okay, at level 0, we have one node. At level 1, we have b nodes. Each of these will have b nodes as children. So at level 2, we have b squared nodes. Okay, and at level 3, we have b cubed, and so on. If I have m tiers, we call these tiers, okay, or levels. So at if the search tree has m tiers maximum, then at the deepest tier, we will have b to the power m nodes. Okay, so remember these things because we will use them in calculating the time and space complexities. Okay. Now, of course, the solution can appear at various depths. So, for example, we will indicate the solutions by the pink or red circles. So here is the solution. Here is another solution to the same problem. Now, how about the number of nodes in the entire tree? If we assume that we have m tiers, so the number of nodes will be 1 plus b squared plus b cubed, and so on until we reach b to the power m, which is dominated by the biggest power here, which is m. So the complexity here in terms of number of nodes in the entire tree, if we will process the entire tree, then the complexity will be order of b to the power m. So that's generally, that has nothing to do with any algorithm yet. Now, if we want to examine the properties of DFS, or depth first search, what nodes DFS will expand? So if you think about DFS, we will move deep and from the left to the right. Okay, so as we move forward in the algorithm in time, we process more nodes from left to right. Okay, until we reach the first solution. Okay, going deep and from left to right in the tree. So the nodes that we will expand are kind of left prefix of the tree, that left part from the tree, and in the worst case we might process the entire tree. So in this case, then the complexity, as we mentioned in the previous slide, the complexity will be order of b to the power m. In the worst case, of course, in the best case, or on average, it might not take that. Okay, but because we don't know where exactly the solution will be, then here we'll just mention the worst case, which is order of b to the power m. Now, how much space we need to run this algorithm? The space that we need is the space that is needed by the fringe, which is the number of nodes that are in the fringe at any point in time. Now think with me, let me do that this way. Think with me what happens when we do DFS. So when we do DFS, we expand the nodes like this. Okay, let's say that this is the expansion of the first node. Then we take one of these and expand it, right? Okay, so at that point, in the fringe are these nodes and also these nodes. And then take one of these, because these now are the deepest, we take one of these and expand it. And then again take one of these and expand it. And so on. Okay, so we always take one from the current tier and expand it to the next tier, and so on. Okay, now the fringe can have these ones and these ones and these ones and these ones and so on. How many nodes will be in the fringe in this case? Remember, the branching factor is b. Okay, so the maximum of the number of nodes here will be b, here will be b, 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 and so on. So the worst case is to go to the deepest tier of the tree, which means that we have b in every tier. So the space complexity will be b times m. b times m. Okay, remember, the space complexity is the space that is needed by the fringe, which is the in order of number of nodes that are now in the fringe. So in the worst case, we will have b from every tier. So in the worst case, we have m tiers. We will have b to the power, sorry, not b to the power, b times m nodes in the fringe. Now the next property is whether this is complete, whether the algorithm is complete or not. Okay. Now what do you think? Is this algorithm DFS complete or not? Okay, Saad? Yes, very good. If there is a cycle, it will not find a solution. But let's say that there is no cycles, or we prevented the cycles in the tree. Will it be complete or not? Saad? No, I'm not saying limiting the depth. I'm saying that we will prevent the cycle somehow. Okay, we'll talk about that later. But let's say that we prevented the cycles. Let's say that there are no cycles in the search tree. If that's the case, then do we have a complete algorithm in this case or not? Will DFS will be complete or not? Okay, very good. So it will be complete only if we prevent cycles. Okay, but if there are cycles, of course, it will go infinitely into the cycle, as we saw in the example last time. If you remember, the search tree was infinite. Okay, if we didn't prevent the cycles, but if we prevent the cycles, then it will find a solution. Now, is that optimal? Is that algorithm optimal? Okay, someone else other than Saad, please raise your hand. Okay, Hamza. Hamza. Yes. So generally, is it optimal or not? No, it's not optimal. Okay, because it will find one solution. That solution might not be optimal. Okay, so if we look at the example here, this is not optimal, right? Assuming that the coast is uniform, this one is the optimal one, is the best one, but this is not the best solution. But it will find it first and declares a solution at that time. So DFS is not optimal. Okay, it will just find the leftmost solution regardless of the depth or cost. Okay, now we'll switch to BFS, or breadth first search. Again, also I think you heard about this in data structures before, but in the context of solving search problems, let's see how it works. Again, we will do the same example. We start with okay, we'll start with the start state. We'll expand it to DEP. Okay, now all of them are at the same tier. So the strategy of BFS is to expand the shallowest node first. Okay, so the node with the least depth first. So that's completely the opposite of DFS. In DFS, we go deep. We expand the deepest one. Okay, so whatever we will expand will be the deepest. So we expand it again and again. Okay, but in BFS, we select the shallowest one, the one that has the least depth first. Okay, so let's see what will happen if we do that here. Here we have DEP. Of course, all are at the same depth, so we will arbitrarily choose D to be expanded to B, C, and E. Okay, now where is the shallowest one? it should be one of these two. Okay, E or P. So arbitrarily again we will choose E. If we were using DFS, we would choose one of those three nodes. Remember from last time? But in BFS, we'll choose one of these two. So here we'll choose E. So we'll expand it to H and R. Now, which one to be expanded next? It should be the shallowest, which is P here. Okay, so we'll expand it to Q. Notice one thing here. We didn't expand any of the nodes of tier 2 until we expanded all the nodes in tier 1. So it is like going one tier at a time. We expand tier 0 first, then all nodes of tier 1, then all nodes of tier 2, then all nodes of tier 3, and so on. Okay, so now we'll start with tier 3 or tier 2, sorry. This is called tier 0, tier 1, this is tier 2. So now if we go back one step, we have all of these nodes in the fringe. Now we will start expanding from tier 2. We choose B, then C, then E, and so on. Okay, so the search tiers, the search goes into tiers. We start from tier 0, then tier 1, then tier 2, and so on. That's of course completely different from how DFS is working. DFS goes deep first. DFS goes tier by tier. Okay, so it tries to search the space in steps of tiers. So if the goal was reached at tier 1, it will stop. It will not go deeper. Okay, so that's the idea of BFS. Now, what are the properties of BFS? As we did in DFS, we'll do again in BFS. How many nodes we expand here in BFS? If you think with me, as we said, we go tier by tier, right? So we'll expand tier 1 first, tier 0, then tier 1, then tier 2, and so on. Every time we have to process all the nodes at that tier. Okay, so if we are in tier 2, we have to process B square nodes, of course, in the worst case. And in the third tier, it will be B cube, and so on. So if we assume that, so we go tier by tier like that, if we assume that the solution, the shallowest solution is at tier S, okay, then the number of nodes that we process until we reach that node, that solution, will be 1 plus B squared up to B to the power S, which means that the complexity is dominated by B to the power S. Okay, so that search will take order of B to the power S, which is the tier of the shallowest solution. So that's in terms of time. Now, in terms of space, at any time, what will be in the fringe? What will be in the fringe actually is the number of nodes at the tier that I am in, right? And if I just expanded this tier, then all the nodes of that tier will be in the memory, and then I will start to expand one of them. So at any point in time, the number of nodes in the fringe maximum will be the number of nodes in that tier. So the worst case will be again B to the power S, which is the tier of the shallowest solution. Okay, so that's the space complexity. That's the maximum memory needed for BFS. Questions, Abdurrahman? No. You mean when we talked about space complexity? No, space in the time. You mean time? Yes, in time complexity we are talking about the worst. We are talking about the worst case also here, Abdurrahman, because no, it is the worst, because if the shallowest solution is at tier S, we will not go beyond it, right? The algorithm will stop at that point. So that's the worst. If S might be M, by the way, and maybe this is what confuses you. S might be M, But still, in this case, it would be b to the power s, where s is m, is equal to m. But generally, if s is not m, then we will stop at tier s, which means that the time complexity here will be order of b to the power s. Did you get it, Abdurrahman? Yes, the worst case ever will be if yes, but we are talking about the worst case for one problem. Yani if you talk about DFS, okay, let's say that we have these two solutions for DFS, or let me go back quickly. Yeah, here, okay, in this example, we have two solutions, right? One, let's say that at tier S and one at tier M. Now, yes, of course, yes. What problem we have? Okay. No, it's based on the. Okay. Now, going back to BFS, is it complete? Is it guaranteed to find a solution? What do you think? Okay, and so yeses. Okay, why is it complete? Yusuf? Wa alaikum assalam wa rahmatullahi wa barakatuh. Yeah, so if there is a solution, it will find it, right? Again, if there's no cycles, of course. Okay, so if it's finite, then the solution exists and it will reach to it. Okay, we don't know when, but it will reach to the solution. Now, is it optimal? Is it optimal? Will we find the optimal solution? Okay, Yusuf again. Or you still raising your hand from last time? Yusuf, do you want to answer now? Okay, thank you. Ghanem. It will not find the optimal solution. Why? Yes, but if that's the shallowest one, do you think it's optimal now or not? Yani, it will find. Don't you agree with me that it will find the shallowest solution? Yani, the highest solution? Okay. Now, even if it's not shallow, even if it's not very shallow, still this is the optimal solution for this problem, right? Or not? Okay, so you think it's optimal? Okay, no, but optimal doesn't mean that out of what we found so far. It's optimal with the general definition. So it's not optimal. It will take too much time. Okay, now, Ghanem, let me explain this point to you. It might take too much time, but there is no other better solution if it found one. That's the meaning of optimal. And optimal doesn't mean that it will take very less time than other algorithms. Okay, actually, we're not talking about. We are talking about cost here. Okay, so the cost in terms of the solution, it might be very high cost, but the best solution still is the best, whether it's low cost or high cost. Okay, so we are talking here about whether it will find the best solution or not. It might take so much time to get it, but it might not find any other better solution. Okay, so it's not about how good or bad absolutely the solution, but within this search problem, if there is a best solution, and of course there is always a best solution, will BFS find it or not? And the best here means least cost. That's the question. Saad? Yes. Excellent. Excellent. Okay. So we all agree that it will find the shallowest solution. Okay. So if the shallowest solution is really the least is the least cost solution, then it is optimal. But for that to be true, there is a condition. As Saad said, the condition is that each step has the same cost, or let's say cost 1. So if every step has the same cost, then BFS will find the solution. But it's not always the case that every step has the same cost. If you remember last time when we talked about the traveling problem, what is the cost of every step? Is it constant? It's not, right? Because the cost was the length or the distance of the road. So in that case, BFS will find the solution with the least number of roads, but that doesn't mean that this is the least cost solution or the optimal solution. It will always find the optimal solution only if the cost of every step is constant, is the same. Okay, so that's the only case where BFS will be optimal. Other than that, generally, if we say that generally there is a cost for each step and or age in the tree, and it's not constant, then it might not find the optimal solution. So we cannot say it is optimal. So it is only optimal if costs are 1, and inshallah we'll talk about costs later if we have time this lecture, or inshallah for sure next lecture. Okay, I hope now that the difference between DFS and BFS is clear. Let me do a quick quiz here. I will show you demos, okay, and for each demo tell me which search strategy is used for that demo. Is it BFS or DFS? Okay. Let me show you the world here. So the world here is, or the problem here is pathing. Again, there's no food items or anything. I want to go from this position to that position. Okay, and of course the black ones are walls, so I cannot jump over the walls, of course. Type. Now, notice how the search will work, and the steps that are taken by the search algorithm will be indicated by small white dots. Okay, so try to see how the dots are expanded, okay, and thus you will know whether DFS is used or BFS is used. Okay, let me show you the demo now and tell me which one is used here, and of course why. Okay, we'll show it again. Okay, any hands? Any answers? Faisal? BFS. Exactly, very good. Okay, so if we run it again, you will see that it goes through circles. Okay, it's like when you throw a stone in a lake. Okay, you will see that there are waves. Okay, so this is very similar to what BFS is doing. So BFS goes in tiers. So the circles here are the tiers because the algorithm is expanding nodes over tiers. Okay, so this is BFS. Now tell me about this one. Okay, let me run it again. Okay, Ghanem. DFS, very good. Okay, this is DFS. Why? Yes, it doesn't go into tiers, it doesn't go into circles. Okay, it goes deep first, then it might backtrack if it didn't find the path and go deeper in the new path and so on. Okay, so this one is BFS. Sorry, this one is DFS, depth first search. Thank you. Okay, now let's move on. Let me ask you then, between BFS and DFS, when can we say BFS will be better and when can we say DFS will be better? Saad? Yes. Okay, so BFS will be better. Yeah, BFS, breadth first search, will be better if the goal is shallow. Okay, it will reach it first, but and of course it's not deep. Okay, type. When can what else? I don't want to switch. Maybe someone else also sees someone else other than Saad. Sorry, Abdurrahman. Yes, if we expect the goal to be deep, then DFS might be faster because it will reach it faster. The problem with BFS is that I have to go through all the tiers, okay, until I reach the goal. Okay, so if the goal is deep and to the left, then DFS will be better. Okay, now I want to ask you, what if I have limitation in memory? Which one would be better? Yusuf? Which one, sorry? B, breadth. D, okay, depth first search. Why? Yes, so the complexity, if you remember, will be B times M, not B to the power M. Right? So it will consume less memory. It will need less memory. Okay, so if I have a limitation in memory, then DFS will be better. Okay, very good. Now, since you saw advantages for BFS and advantages of for DFS, let's try to combine both in one algorithm. So the idea here is to combine the advantages of both, trying to find something that on average will be better than both of them. So the idea here is to go into iterations. So the first iteration, we will run DFS, because DFS needs less memory, as we said. We will run DFS, but with depth 1. Okay, so we will limit the search tree to depth 1. What does that mean? It means that we will not expand beyond the level 1, beyond tier 1. Yani we will assume that nodes at tier 1 have no children. And then see if we found a solution, then we are done. If we didn't find a solution, we increase the depth limit to 2. So we run another iteration, but with depth limit 2. We run DFS, but now instead of depth 1, we will increase the depth to depth 2. So now within the limit of 2 tiers, we will do DFS. Remember, we are not doing BFS. We are not going tier by tier here, but we are increasing the limit that we can reach in the search tree every iteration. Still, we are doing DFS, but we are doing DFS through iterations. So if we found the solution at that level, we are done. If we didn't, then we increase the depth limit to 3. Now we have 3. We have bigger search tree. Within this bigger search tree, we go using DFS, because DFS probably will be faster to find a solution, generally. Okay? Or at least it has less memory requirements. So we try with DFS, but within depth limit 3. And then within the depth limit 4. Now, if for this example, we will find the solution at depth 4, so we will stop. Okay? So you see the difference now between BFS and DFS and iterative deepening. In iterative deepening, from the name, it goes into iterations, and with every iteration, we are increasing the depth of the tree. Iteration 1, we limit ourselves to depth 1. In level 2, we limit ourselves to depth 2. Type. When we limit ourselves to depth 2, what does that mean? It means that whenever we reach a node at depth 2, we will assume that it has no children, which means that we'll have to backtrack and go deeper from another path, and so on. Okay? So that's the idea. Now the question is whether this is a waste of time, because it seems like we are doing some processing repeatedly. For example, some of the nodes that are at level 3, at tier 3, will be processed in iteration 3 and also in iteration 4, because we are doing depth first search from the beginning. Okay, so there are some repetitions, right? There is some redundancy between the iterations. Some of the processing of iteration 2 was actually done also in iteration 1, and some of the processed nodes in iteration 3 will be already done in iteration 2. So there is some redundancy. Okay, but the question is whether this is really bad or not in terms of time. I think the point here is that it's not that bad. It's not so bad. Why is that? Because if you remember, most of the work will be at the lowest level, okay, or the deepest level. Remember, the number of nodes in the deepest level dominate the number of nodes in the entire tree. So the new nodes that we will process will be of good number anyway. Okay, so we'll be dominating this the complexity. So yes, there is redundancy, but it's not so bad. Okay, still we are processing new nodes, and most of them will be in the new tier, which has much bigger number of nodes, because as you remember, the number of nodes in each tier increases exponentially. So the time will be dominated actually by the nodes at the newest level every time. Questions, Faisal? No. Okay, let me try to explain it again. Okay, let's go back. So the idea here is that forget about BFS. Okay, we are not doing BFS at all. Forget about it. Okay, but think about it as doing DFS, but to different tiers or different depth of the tree at every iteration. Okay, so there is no BFS at all here. The concept of BFS generally is there, but we are not running BFS algorithm. Okay, what we are running actually is DFS, but we are running DFS on different trees every time. So in every iteration, we increase the depth of the original search tree. In iteration 1, we assume that the tree is of depth 1 only, and we run DFS. We might find a solution. In this case, we are done. If not, then we expand the search tree. We run DFS from scratch, but now with depth 2, with the tree at depth 2, with the limit at depth 2. Okay, so we start again from the root, and now in the second iteration we can go to depth. We can go to tier 2. We are allowed to go to tier 2, but we are not allowed to go beyond tier 2, which means that if the solution is at tier 3, we wouldn't reach it until we get to iteration 3. So now because we are running DFS in iterations with increasing the depth, that means that we will find the shallowest solution first. So that's the spirit of BFS. Okay, that's the spirit of BFS, that we will find the shallowest solution first. But we are also using DFS, which means that we don't need lots of memory. So that's a mix between finding the shallowest solution first, okay, because that sometimes is good if the cost is uniform, and having good memory footprint or memory requirements, which is DFS guarantees for us. Faisal, do you understand it now? Okay, I think it will be much more clear, and I would recommend that for everyone, is to go back to the example that we used for BFS and DFS, okay, and try to do it using iterative deepening, and see what will be the order of nodes that are processed, and compare that with BFS and DFS. You will see the difference in the three cases. Okay, so please do it as an exercise. Okay, Abdurrahman. You don't need to start from where you stop, but maybe you can avoid going through the same actually I don't think it is easy to remove the redundancy, because even if there is a node that you reached before, but maybe you stopped at that node because the depth was reached, but now in the new iteration you have more depth, so you might need to expand it now. So I don't think it will be easy to avoid redundancy here. Okay, there might be some ways, but I don't think it's straightforward, and maybe not at all, because as I told you, in every iteration the search tree is different. Okay, so even if you reach it, yes, even if you reached a node and that node was not a leaf in the original search tree, if it's a leaf in the original search tree, maybe you should not get back to it, okay, because it's a leaf anyway in any search tree. But if it's not, and you just stopped at that node because you were limited by the depth, then you have to expand it in the new iteration. So you cannot just say, I reached it before, I should stop. Okay, Hamza. Okay, Said. Okay, okay. What is the point of processing it again? The point of processing it again is that now you increase the depth of the tree, so you might find a solution from that node. Maybe in the previous step you stopped because you were limited by the depth, but now the depth increased, right? So you might find a solution from that node, even if you process that in the previous iteration. Yeah, the search tree changed. Okay, so you cannot say that you saw this node before, you should stop at that. No, the search tree changed by adding a new tier. So by that tier, you might find a solution. So you have to process it again. Okay, I hope Said will that will be clear. If not clear, please take the example and do it. Okay, but you need, of course, to understand first the steps. I think the steps are clear, but maybe the idea is not clear of why that could be good. The idea is maybe in a different way, that you want to use how fast DFS is at some times, and also the space complexity, or the good space complexity of DFS, but you also at the same time want to reach the shallowest solution. So you don't want to go deep in the tree while there is a shallow solution. Okay, so you want to do a mix, and that's a kind of a mix. Okay, I think it will be clear if you do it, inshallah, on your own by the same example that we saw earlier. Last question by Ridwan. Yes. tell me, what is the space complexity here? No, the space complexity is the number of nodes in the fringe. Okay, so at any point, the space complexity will be the space complexity of DFS, because we are running DFS. Okay, and once we go into a new iteration, we just ignore the memory, ignore whatever in the fringe, and we start from scratch. So at every time, the space requirement will be the space requirement of DFS, which is b to the power, not b to the power, b times m, which is much less than BFS. You're welcome. Okay, so we'll have to stop here. In a summary, we went through 3 algorithms: BFS, in the order of explanation, DFS, BFS, and iterative deepening. All of them don't consider the cost of the steps. Okay, so we don't care about the cost of the steps at all in all of these 3 algorithms. Inshallah, in the next lecture, we will start to see algorithms that consider the cost of on the edges. Okay, the first one of them is called uniform cost search, and inshallah we'll study it first thing next time. So talk to you inshallah on Tuesday. Assalamu alaikum wa rahmatullahi wa barakatuh.